Good morning, everyone. Welcome back to Early Morning Calculus, brought to you live from Grand Rapids Community College. Happy you could join us once again. And what do we have planned for today? Oh, lots of good stuff. This is the official agenda for Friday, April 11. Okay, number one, we have to check the homework in 10.1, and then we have to finish section 10.2, and hopefully begin sections 9.1 and 9.3. They're kind of combined there. Okay, we do have some even answers in 10.1. I believe there was an even as in 32. And in number 32, they wanted you to draw a triangle. Well, what I can tell you are the parametric equations to get segment AB. That would be one side of the triangle. And for that one, I got x equals 1 plus 3t. And the y to go with that was 1 plus t. And then to get segment AC, another side of the triangle, you had a graph x equals 1 and y equals 1 plus 4t. And finally, to get the side BC, you had to graph x equals 4 minus 3t. That's for the x, along with 2 plus 3t. And then what did it look like when it was finished? Well, you kind of get a triangle sitting something like that in the first quadrant. This would be the point A. This would be the point B, and C would be up there. You get that exact triangle if you keep t between 1 and 0. Just like it said in exercise 31, as long as t ranges between 0 and 1, these parametric equations will do line segments. And in this case, the three line segments all joined together and made a nice triangle. Okay, I believe that was the only even in that particular section. That was 10.1, of course. Do you have any questions for me from 10.1? Where you had to draw graphs of parametric equations, convert them to Cartesian, and do a variety of things. Anything that we should check this morning? 10.1.
Check 710.
Which one?
710.
Okay. Problem 17. Okay, in problem 17, x equals sinh of t, and y equals cosh of t. Okay, what kind of functions are these? You recognize them? Hyperbolic functions. Okay, when we studied hyperbolic functions, we noted that the properties of hyperbolic functions were a lot like what? Trig functions. And that's why when I took calculus, they called them hyperbolic trig functions. They added the word in. Now it just got shortened to hyperbolic functions. The reason I bring that up is we probably have to do something similar to what we would do if we had trig functions. Now, if you have trig functions and you want to convert parametric to Cartesian, you remember how we started that kind? See, normally we take one equation and solve for t and then substitute in the other one and then we're fine. But if we wanted to substitute in here, we got to get into inverse. So rather than do that, what did we do when there was trig involved? Yeah, we tried to find some identity that related the two, and then we substituted into that. All right, going back to here, I have sinh and cosh. Is there an identity that relates sinh and cosh together? Yes, there is. Long time ago, cosh squared of t minus sinh squared of t equals 1 was a hyperbolic trig identity. And that could be looked up if you had to. But the key is you have to realize with this kind you want to start with some kind of identity, because then you don't have to get into all that inverse stuff when you solve for t. Now, if cosh is equal to y, then what's cosh squared? And sinh squared? And we're there. That's it. So you got to kind of store in the back of your mind if there's trig involved, or in this case hyperbolic functions involved, which act like trig functions, start with an identity that relates the two functions together. And there's always something you can use. What if I had x equals sinh and maybe y equals tanh? Is there a trig identity to relate those two? Yep. Tanh of t equals sinh of t over cosh of t, and then you could maybe go from there. So there's different things that you can do. Of course, once you know sinh, you got to figure out what cosh is, but you can get that by using this one. So I'd probably use this one along with that one. And then you can substitute in. For tanh, you can put y. For sinh, you can put x. And then you got to figure out what cosh would be. But back in the hyperbolic functions, we did problems where if you knew sinh, how do you get cosh? Well, you go back to here. See, cosh squared minus sinh squared. Hope I didn't open a can of worms here. Equals 1. So cosh squared equals 1 plus sinh squared, right? But what's sinh squared? So this would be x over 1 plus x squared. So y equals this would be my Cartesian. So whenever there's trig involved, or in this case hyperbolic functions which act like trig functions, use identities to get to the answer is the recommended procedure. Okay, anything else you wanted to check? From 10.1. Anything else that didn't quite make sense? Could you,
Looks like 45.
which one, 45?
Yeah.
Okay, that's kind of a fun one. They wanted you to graph these simultaneously. So we'll get out our calculator and set it in simultaneous mode so you could watch the particles collide maybe. All right. So we'll get our calculator and type in the equations. So this is doing problem number 45. And yep, I'm still in parametric mode, so it's ready to go. They first want me to type in for x1 3 sine t. I can do that. And then to go with that one is 2 cosine t. Okay, then for the second set of parametrics, it's -3 plus the cosine of t, and it's 1 plus the sine of t. And they said do them both from 0 to 2 pi. Okay, from 0 to 2 pi, that's standard, isn't it? So I could get that part if I just went f(2,6). The problem is I'm drawing the first one, which is an ellipse, okay? And then it draws the second one, which looks like another ellipse. Now, to see what their shapes really are, which is not that important, you can go zoom 5. And the first one is indeed an ellipse, because when I square it off, it looks like it. The second one is a circle, right? But that's kind of a small picture, so let's try to magnify it a bit. And to do that, I can cut down on the max and mins. For this one, we'll go -5 to 5, maybe. And then the other one, maybe -3 to 3 would seem to include it. Let's see. Okay, that's a pretty good view of that one. And then a view of that one. Okay, but how am I going to see whether they collide or not? I got to graph them simultaneously. So under F1, remember 9 is graph format? And if you go to the second entry, it says I'm graphing how? Sequentially, that means first one, and when that's done, the other one. If you arrow to the right, number 2 is simultaneously. You press enter, and now watch them. See? They're graphing at the same time. Isn't this fun? And all of a sudden, bang! Oop, they missed there. So was there a collision point? Where does it appear to be? Right there on the x-axis, right to the left. It looks like about how many units? 3. I'd guess -3,0. Now they wanted you to verify that in the next one. So first they wanted you to watch and see if there was any collision. Did you see it collide? Well, they should have splattered the leading cursors, you know, to show it, but the calculator didn't do that. They just kind of passed through each other. Okay, so yes, there are 2 intersection points. That was the first question, right? And the second question is, are any of these intersection points collision points? In other words, does the particle get there at the same time? Well, for you guys, that's fairly easy to determine because you can set the leading cursor on. You can set them on simultaneous graphing and watch, right? Do they ever come together at the same point at the same time? Okay, now in the old days, how did we do it? Well, we first had to find the intersection points, and then we had to see if any of these intersection points were arrived at the same time. That means same t value. And that's what we're going to do in just a second. But before we do, we can't let our newcomer miss out on what happened, because this is exciting. So we're going to run this again. And F4 is regraph, right? This is number 45. We're checking to see if these curves ever collide, because there's particles racing around these 2 tracks and they intersect. So here's the regraph. Here it comes around and all of a sudden, crash. And they were wondering if there were any collision points, and we decided there was one out there on the x-axis. Now, if you couldn't see it, and it wasn't a nice point like -3,0, is there a way to find that collision point? Okay, this is doing it mathematically. This is what we used to do before there were calculators. Okay, here are the parametric equations for 45. Okay, for the first curve, we were graphing x1 equals 3 sine t. along with y1 equals 2 cosine t. And then my second curve was x2 equals negative 3 plus cosine t, along with y2, which is 1 plus sine t. Okay, now to have a collision point, there has to be an intersection point first, right? And the particle has to arrive at that point at the same time, okay? Well, first I have to find where they intersect, and then I'll check to see if the t value is the same. Well, what has to be true if you're going to have an intersection point? Well, doesn't x1 have to equal x2, and y1 has to equal y2 at the same time to have an intersection point? Well, if x1 equals x2, then 3 sine t has to equal minus 3 plus cosine t. And for the second one, 2 cosine t better equal 1 plus sine t. But these have to happen at the same time, don't they? So it's like solving a system of equations like in algebra class. And one way we did that was using substitution. So we can take the first one and solve for cosine t. 3 sine t plus 3 has to equal cosine t, doesn't it? All right, now we can take this and substitute in that one. So we keep the 2, and what can we replace cosine t with? 3 sine t plus 3. And that has to equal 1 plus sine t. But you remember your algebra, right? If you want to solve two equations at the same time, you can use substitution method. I solved for cosine t, and then I substituted for that in this one. Now I can solve for t. You end up with 6 sine t plus 6 equals 1 plus sine t. Combining like terms, you end up with 5 sine t equals negative 5. What does that make sine t? Now, I'm working strictly in here, right? That's was my t window. So, is there a t value somewhere between 0 and 2 pi where the sine is negative 1? When is sine equal to negative 1? Right, 3 pi over 2. I wonder how this course will go when trig is a prerequisite for it. Think it'll go better?
I had trig, it was horrible.
Oh, you had trig and it didn't help. Well, you see, we got this thing, right? So, I don't feel too sorry for you. Except it's going to take forever if you don't know your basic trig values. But you got that pink sheet. You could look it up on there. You could go F2, solve. The only problem is there's an infinite number of answers, and you may or may not get your answer out of this. But it will solve sine, sine of t equal to negative 1 for t. But see, it gives t as 2n pi minus pi over 2. That's 2n pi minus pi over 2 is what the answer is. Now that may or may not get you where you want to go, I don't know. But if you have 2n pi minus pi over 2, what if you let n equal 1? then you get 2 pi minus pi over 2, which is now if you let n equal 2, you get 4 pi minus pi over 2. What's that? 7 pi over 2. Would that work too? Yeah, it's just that my answer had to be where? So that's why I picked that one. Okay? So, according to this, I get a point of intersection when t is 3 pi over 2, right? Now, am I going to get a collision point there? Well, I should, because one t value produces the same point twice, right? What is that point? Well, now you can go back up here, and x1 would be 3 sine 3 pi over 2. Isn't that minus 3? And y is going to be 2 cosine 3 pi over 2, which is 0. So where's the collision point? Minus 3, 0. Would you get the same thing if you plugged in the second one? Yes. If you went to the other point up here, x2 is going to be minus 3 plus cosine 3 pi over 2. That's minus 3 plus 0. Yeah, that's minus 3. Same x coordinate. And y2 is going to be 1 plus sine of t. That's 1 plus sine of 3 pi over 2. Hey, that's 1 plus negative 1. Hey, that's 0. So when t is 3 pi over 2, what happens? Both curves are at exactly the same point at the same time. Collision point. Okay? And then part C was, okay, what if you change the equation slightly? In other words, you left the first two the same, but on the second two you changed them to this. 3 plus cosine t, and the y2 is 1 plus sine t. And basically what happens is you get the same curve, of course, on the first one, but the other one moved over to here. Okay, it's on the other side of the picture. And then if you run those two, they still have two intersection points, but they don't collide anymore. Is that sufficient? I mean, that's not every detail, but that's the bulk of it. He says he's okay. All right, were there any others in there that were a little confusing that we should check out? Or were the rest of them pretty straight? Did you do okay on 31 and 32? Did they work out for you?
We do 31.
31, where they say, show that these actually do work? Okay. To do that one, you have to remember there's two ways to write an equation of a line. The one we all use, and the one we used to use before calculators came around. You say, what is he talking about this time? Just jabbering. Here's problem 31. To help you see how this works, we have to do our General Motors trick first. If I ask my students for an equation of a line in general, today 99.3% of the students will say this. When I asked your parents the same question 30 years ago, they gave me this one. Which one is right? Both. Well, why did your parents give me that one? Because if you want to find the equation of a line, you can direct substitute right in there. The point is x1, y1, and put in your slope and you're done. Whereas this one, you find your slope, and then you gotta write it down, then you gotta substitute a point in, then you gotta work backwards and find b. What made the transition happen? Calculators. So you see, calculators demand you type it in this way or it won't graph it. So technology kind of took over, and most people don't even remember that one. But to see this problem, if you can remember this is an alternative equation of a line, it's going to make this problem easier to do. Okay, so that's my recall part. Have you ever seen this? Yeah, when I mention it, people say, I remember that one. Yeah, we just never use it. And even instructors kind of give up and just go with that one. Because if you go with that one, then you got to answer 20 more questions and you just want to get the problem done. Okay, but this is going to make this problem a little easier. Okay, this is the claim. They're saying if you do x equals x1 plus x2 minus x1t along with y equals y1 plus y2 minus y1t. They're saying this is an equation of a line segment from x1, y1 to x2, y2. And that works, they said, if you keep t between 0 and 1. Okay? So they're saying if you wanted just to draw the line segment with these endpoints, you can use these two equations and set your t from 0 to 1, and it'll start here and stop there every time. They want you to show why. Well, first of all, a line segment is part of a line, isn't it? So the first thing we have to show is that these convert to a Cartesian equation which represents a line. And then we have to show if we stick from 0 to 1, we start at one endpoint and stop at the other. So there's two things to show. Okay, part 1, we're going to convert these two equations to Cartesian form. Okay, how do we do that? Well, in the old days, we would solve for t and substitute into the other one. So we're going to take the first equation here and solve for t. Well, first I subtract x1, and I get this. Then solve for t, and what do you get? X minus x1 over x2 minus x1. Okay, I solved the first equation for t. Now I substitute into the second equation. Standard way to convert. Solve for t in one equation, substitute for t in the other one. The exception? Trig. We don't do that for trig because then you got to work with inverse trig functions, so we use a trig identity instead. All right, taking the second equation, I get y equals y1 plus y2 minus y1 t. Put that t in there and see what happens. Well, I can subtract y1, right? And I can put in y2 minus y1, and then in place of t, I put x minus x1 over x2 minus x1. Okay, continuing with that thought. I can rewrite that as y2 minus y1 over x2 minus x1. In other words, put this under him instead, and then I'm left with x minus x1. Is that move okay? From here to there? And it doesn't matter which one it's under, right? Why did I want it under him? Because you're supposed to look at that and say, ooh, I know what that is. That's slope. So what have I just shown? That if you convert those parametric equations to Cartesian form, you get the equation of a line, right? You get an equation of a line. In fact, it's the line that goes through x1, y1. All right, now what do you have to do? You have to show that if t runs from 0 to 1, you're going to start at x1, y1, and you're going to stop at x2, y2. Okay, so we start by letting t equals 0, because that's where it starts, right? All right, going back to the parametric equations, which are now right at the top of the screen here. We're going to let t equal 0 and see what x becomes, okay? All right, x is going to become x1 plus x2 minus x1 times 0. Well, what's that? So, if you start at 0, are you starting at x1? Is the other coordinate y1? Well, I don't know, let's try it. And what does y equal? So you see, if you set the parameter from 0 to t, you're going to start with 0, and if you plug in 0 for t, you can see you end up at x1, y1. All right, now you replace t with 1 and show that you end up at x2, y2. That's 31. So you had to verify that this is a handy little set of equations if you want to produce line segments. And then I had to assign 32 because that means you can draw a triangle using parametric equations. Did you do it? Is it kind of neat? I thought it was. All it did is just draw the segments that form the triangle, and they all met, and that's all you got. Provided you set the parameter from 0 to 1. If you did more than that, then you got more than just the line segments. Okay. Anything else from 10.1? We covered it pretty much to your satisfaction. Not too bad. We assigned a couple just that were a little more interesting. You had to maybe think just a little bit harder, but basically parametric equations are kind of neat. They're kind of fun. And then what did we do? We went to 10.2 and took the fun away. Because we said, okay, now that you know how to do parametric equations, what if I have to do calculus with them? Which means what? Take derivatives when they're parametrically given, and integrals, which is what part of the topic is today. How do you integrate when they're given parametrically? Okay, we weren't quite finished with the derivative part, but we did at least come up with a way to find the derivative if they're given parametrically, right? So we'll refresh our memories on that part. If x is given as a function of t, and y is also given as a function of t, then if I want to find dy dx, how can I do it? Well, you can write it two ways. You can start by taking, I think we got this far, didn't we? Yeah, you take dy over dt and divide by, we derive this. Or, in essence, it just means do what? I mean, how would Newton write this? Take f prime of t and divide by g prime of t. Same thing. Okay, then we proceeded to find the first and second derivative for a set of parametrics. But I don't think we had a chance to finish that problem, did we? So I kind of saved what we did before. We were doing this application. Our parametric equations were x equals sine of 2 pi t and y equals cosine of 2 pi t. And here you see us following the formula, doing the first derivative, and we ended up with that. Okay? Well, to find the second derivative, we use this formula. You take the derivative of y prime and divide by the derivative of x with respect to t again. So you notice the denominators are the same, but the numerator was the derivative of the derivative, and the derivative of minus tangent of 2 pi t was minus secant squared of 2 pi t times 2 pi. And then we simplified it, and we ended up with this for the second derivative. Okay, there was a second half to that problem, though. And it said, find the equation of the tangent line to the curve at the point where t is minus 1/6. Okay, that's a standard question in Calc 1 that's on virtually every test. Find an equation of a tangent line. Do you remember how we did it back then? Equation of a tangent line? Well, we needed a slope. We actually gave in to the student pressure and we said we need to find y equals mx plus b. And how do we find m? In calculus, how do you find the slope of a tangent line? You take the derivative, you evaluate the derivative at the point of tangency, and that's your slope, and then you finish it like you normally would in algebra. Well, where do I want my tangent line to be located? At the point where t is. So, can you see a plan evolving here? I'm going to take the first derivative of the function. Now I'm doing it parametrically, right? And then I'm going to plug in my t value, because that's where the point of tangency is. And that should give me the slope. And then I'll just do my standard y equals mx plus b and finish it. Are you ready? Doesn't matter, we're going to do it anyway. Okay. All right, so we're looking for y equals some mx plus b, right? But to get m, I have to go to the first derivative, and I have to evaluate it when t equals negative 1/6. That's what m's going to be. The value of the first derivative evaluated at the point of tangency, which occurs when t is minus 1/6. Okay, you may or may not recall that we've already done the first derivative. Do you remember what it was? It was negative tangent of 2 pi x t. Okay, I think that's what we got for the first derivative. Does that look familiar? So, if I want to take the first derivative and evaluate it at t equals minus 1/6, I'm going to get minus tangent of 2 pi times minus 1/6. Uh-oh, trig again. I wonder if we can come up with that. I'll bet the calculator knows that one, even if we don't. I need minus the tangent of, well, if I fix it up, that looks like minus pi over 3 to me. And what's the answer to that? Well, in the old days, we say, well, everybody knows what sine of pi over 3 is. That's square root of 3 over 2. And everybody knows cosine of pi over 3. That's 1/2. And square root of 3 over 2 divided by 1/2 is square root of 3. But I'm in quadrant 4, so it's going to be negative square root 3. And negative square root 3 would be square root 3. Is that what the calculator said too? Which do you like better? I know, you're the modern generation. Use a calculator even if it takes more time. right? So even though text messaging is the most inefficient way to communicate anybody ever designed, I'm going to do it rather than just talk on the phone because I look cool if I do it. So as long as it means cool, I'll do anything, even take 3 times as long to communicate if I can look cool.
I don't think using calculators is cool.
You don't?
It's not very hip.
Well, that's my point. Now, if we can make math cool, then everybody would just want to do it. So, what's the secret to math education? Make it cool. Because we've already proven if it's cool, people will go way out of their way and take 3 times as much time to do it just to be cool. Now, I don't text message because why would I? I can just dial somebody and talk directly and take 1/3 the time to get my message across. Well, what if they don't answer? Duh, leave a message. Okay, next. What does square root of 3 represent?
The slope.
Oh, the slope. So now officially y has to equal the square root of 3x plus b, right? Oh, now I have an issue. How do we normally find b? We plugged in a point. Which point? The point of tangency. I don't know the point of tangency. Yes, you do. It's t equal minus 1/6. That doesn't give me the point. That just tells me the value of t. So what do I have to do? Go back to the parametric equations, which happen to be this pair. And let t equal what? Negative 1/6. So that implies at the point of tangency, x is going to be the sine of, negative pi over 3. And y is going to be the cosine of negative pi over 3. Out with the calculators again. What's the sine of negative pi over 3? Negative square root 3 over 2. What's the cosine? Right, 1/2. Okay, now I'm ready to finish it. So going back to here, I can put 1/2 in just like we normally did in the past. I can put minus square root 3 over 2 in, and now I can solve for b. I ended up with 1/2 equals negative 3/2 plus b. What does that make b? So guess what the final answer is? Y equals the square root of 3x plus 2. There he is. Final answer to that particular problem. Okay, in Calc 1 though, I'm surprised they didn't ask us to do that on this one. But in Calc 1, they always said, okay, draw it and see if it really worked. The problem is, my original function is given parametrically, isn't it? But this one is not. How hard is it to convert this to parametric form? It's real easy. Let x equal what? T. You did catch that the other day, right? And then y would be square root of 3t plus 2. There's a parametric form for that. It's not the only one, but it's the quick one. Okay, let's see if we actually did okay. Now, where was the point of tangency? Well, it was when t was minus 1/6, so we got to make sure our window includes minus 1/6, right? Otherwise, we still won't see it. Getting rid of some of the old stuff. And we are ready. First of all, the original function was sine of 2 pi t. Excuse me, there's the x, and then the y. Cosine of the same thing, 2 pi t. And then my tangent line, well, for that one we let x equal t, and we let y equal square root of 3, and then t, and then plus 2, right? Now, if I just did the standard window, and I'm going to do that in a minute, but I want you to tell me what's going to happen. Well, the standard window goes from 0 to 2 pi, and my point of tangency occurs where? At minus 1/6? That's not in there, right? So if I do that, what am I going to miss? Seeing the tangent touch the curve. Let's try it. F2, 6. It sure wants to go around the curve a few times. There it is, right? What's the problem? I can't see if I got a good point of tangency or not, because the point of tangency was not included in the t value. All right, so now we're going to play it a little smarter, and we want to make sure minus 1/6 is in between. So maybe we could go from minus 1 to 1. Should that include the point of tangency, minus 1/6? It's almost right in the middle even, right? Okay, plus the picture was kind of small, wasn't it? So let's go from minus 2 to 2, and minus 2 to 2. I might be cutting it a little close there, but we'll see. So here's the graph. Oh yeah, that was a great picture. What do I have to do? Slow down the t, right? Okay. Before I do that, though, I want to turn off the simultaneous. Of course, as soon as I do that, it draws the first one and then draws the second one. Terrible resolution. I mean, it looks like there might be some hope here, but we know how to get better resolution. Slow this down. 0.02. That'll slow it down, right? Okay, now let's see if we get a better picture. That one's still moving fairly fast for a 0.02. And because of my t, it is going to go around more than once, but we can live with that. We had to get the t like that in order to get the tangent line in. Does it look like it has hope? The only thing is, I would have liked to see a little more of the lower portion. So I went back here and changed it to minus 2 and then to 1, because the upper part was fine. And then I looked at it one more time. Talk about not having a life. You get such a charge out of watching this that you keep changing the t so you can look at it more. And you can watch this particle just to travel around that oval track. Look at it go. Speeds up a little on the horse. Look at how it speeds up. Notice that movement, and then it goes, the steeper part slows down. Speeds up again. Oh, quit. Here comes the nice tangent line. Look at that. Just sit back and enjoy on a rainy Saturday. Does it seem to work? Oh, indeed. I could gaze at that for 10 minutes, but I won't. You say, go ahead, we'll take a nap, wake us up when you're done. It does work, doesn't it? I always like it when it works. I don't know. That's motivation. When things work. When they don't, that's not motivation. But, okay, we have to do a little bit more with the calculus. That's the typical derivative application. Okay, how do you find the derivative? How do you find the second derivative? And the most famous application from Calc 1 was find an equation of a tangent line. So we did. Okay, now we've got to move to integration. Oh, there's another problem we have to do first, but we're going to move to integration. And what was the famous problem that gave rise to the integral? The area problem. Remember, we were looking for area under a curve or something? That's what we're going to do in parametric form. Try to find area under a curve, which means we got to integrate and all that fun stuff. Okay, but I had another problem here. I'm sorry, I forgot about it. It has to do with derivatives. It was another popular problem in Calc 1. It was the problem where we had to determine all points on the curve where you have horizontal or vertical tangents. And we're going to do one like that in parametric form. Before we do, however, what's the characteristic of a horizontal tangent? Right, slope of 0. What about vertical tangent? Undefined slope. So when we did a problem like this in Calc 1, we looked for where is the derivative equal to 0, and where is the derivative? What caused the derivative to be undefined? Division by 0. Okay, keep that in mind as we go through this. Here's the problem. Here it is, so you can see it. Okay, in Calc 1, even if you didn't have any idea what to do, you always got some points if you did what? Took a derivative. Okay, so we're going to do a dy over dx, okay? And the way we do this is take the derivative of y with respect to t and divide by the derivative of x with respect to t. Okay, x is right there on the screen. What is the derivative of x with respect to t? Right, 3t squared minus 6t. Derivative of x with respect to t. 3t squared minus 6t. What about the derivative of, I want him on the bottom. I don't want him on top. On top I want the derivative of y with respect to t. Okay, what's the derivative of y with respect to t? 3t squared minus 3. Okay, number 1, find t so that this derivative, 3t squared minus 3 over 3t squared minus 6t equals 0. I want to find t so that that happens. Well, how do you solve an equation like that? Yeah, you get rid of the fraction, so it's 3t squared minus 3 equals 0. Man, how'd we go from there to there? Magic? No, we multiplied each side by the common denominator, and something times 0 is 0. Okay, how do you finish that? Probably the square root property. We went 3t squared equals 3, and then t squared equals 1, so t is... So, don't forget to answer the question, though. What was the question? Find all what? Points. I only found the t value, so now what do I have to do? Plug those numbers in and see what the points are, okay, right here. If t equals 1, what does x become? 1 cubed minus 3 times 1 squared, which happens to be? Right. Y is going to be 1 cubed minus 3 times 1. What's that? Well, that's minus 2 as well. So what's one point where you ought to have a horizontal tangent? Minus 2 minus 2. Okay. Secondly, if t equals minus 1, x is going to be negative 1 cubed minus 3 times negative 1 squared. What is that? Pardon?
Minus 4.
Okay. And y at the same time is going to be minus 1 cubed minus 3 times minus 1. What's that? So, where do you have horizontal tangents? you should have one at minus 2, and you should have another one at minus 4, 2. And we can, of course, check that, right? By drawing the graph eventually and see if it looks like you really have them there. Okay, part 2. I have to find t so that the derivative, 3t squared minus 3, all divided by 3t squared minus 6t, is what? Undefined. What makes that expression undefined? That's the derivative I got. What's going to make it undefined? The denominator equal to 0. Okay, we can factor that one. Take out a 3t and you're left with t minus 2. So you get t equals 0 and you get t equals 2. So it looks like there's two spots where you might have a vertical tangent. But again, they want to know the points. So therefore, if t equals 0, what's x going to be? Yeah, it's going to be 0 cubed minus 3 times 0 squared, which is 0. What about y? That's the same thing. So it looks like you ought to have a vertical tangent at 0, 0. Okay, you also get one when t is 2. T equals 2, x is going to be 2 cubed minus 3 times 2 squared. That's 8 minus 12, which is minus 4. Okay. Y is going to equal 2 cubed minus 3 times 2. That's 8 minus 6, which is 2. So that would produce the point minus 4, 2. So you're supposed to have a horizontal tangent where? At minus 2, 2, minus 2, minus 2, and minus 4, 2. Hey, wait a minute. How can a curve have a horizontal tangent and a vertical tangent at the same point? Something's messed up here. Well, you mean the curve spins around and maybe crosses itself? And going one way, it's horizontal, and when it comes back and crosses itself, it's vertical? I got to see that. This is weird. It says that minus 4, 2, you have both a vertical and a horizontal tangent. I got to see that. Because it's just one curve. How can one curve have two different tangents at the same spot? Weird. Okay, I got to get rid of my beautiful picture here. Oh well. Just like everything else in life, it can't last forever. And now you got to type in the new parametrics. Okay, one is t raised to the third and minus 3t squared. And the y partner to go with it is t to the third. And that one was minus just plain 3t. Okay, we'll try the standard window first and then kind of go from there. F2, number 6. Here comes the curve. Oh yeah, I can see that. Yeah, just like the calculus showed, I can see the vertical and horizontal tangent. This stupid curve doesn't even cross itself. So now what? Like change the t's. Maybe if I go from minus 2 pi to 2 pi, I'll see more of it. Are you ready? Here it comes. Oh, there goes the curve. He's rounding the corner. He's turning. He crosses himself and goes. Ah, now I can see. We had a vertical tangent at 0, 0. Does it look like that might be true? There was another one at minus 4, 2. That would be a tangent on the part of the curve that goes up, right? In other words, that way, vertical on that part. But coming in, at the same point, it looks like it might have been, and then there's another one down here, right? So two horizontal tangents, one there, two verticals, one there, and one right there. So those two curves actually intersect each other at perpendicular, right? Do you remember what you call two different curves that intersect themselves at right angles? That means the tangent lines at the point of intersection are perpendicular. It's that dental type term, you know. Orthogonal. Dentists use that, don't they? Oh, that's orthodontal. Oh. But last time I went to the dentist, they said, your mouth needs some work. Your teeth are becoming orthogonal. Okay, this curve is orthogonal to itself. Who cares? I don't know. I just thought I'd bring that up. Okay, the next step is now to check out integration with parametric. And we do that in the context of finding area. Do you remember a long time ago when you were looking for area under a curve? We divided it into rectangles and used that area, and then we summed them up, and that eventually turned into the integral. Okay, so if you want to do integration with parametrized curves, then you probably might want to look at an area problem, just like before we looked at a tangent problem. Okay? That's why this is next. Finding areas under parametrized curves. Okay, theory. Well, first they want you to do a recall. Because if you had a function y equals f of x, and the function stayed greater than or equal to 0, that's all the way from A to B. So if this is A and that's B, do you remember how we found this area? We took an integral from A to B, didn't we? Of f of x dx. That's how we did it. Okay, now I want to convert that method to something that would involve parametric equations, okay? Okay, it says, if the curve is also represented by the parametric equations, where x equals some f of t and y equals some g of t, and that's where t goes from alpha to beta. So the t values are from alpha to beta, okay? Then what does the area under the curve become? Well, we're going to start with what we recalled up here, right? So in Cartesian, I do it this way. Okay? But wasn't f of x just the y? Y equals f of x? So I substitute and put y here instead. Now we don't do that in Cartesian because we want to work with f of x, which has an x in it, to match this. But when we were doing practical applications like in solids of revolution and stuff, quite often we'd have a y here and an x there, and we'd have to convert to x. But this time I want to go the other way. How come? Because this could be the integral, and I'm going to switch from alpha to beta because I'm going to go in t language. What can I replace y with? Well, y is given parametrically as g of t, right? What can I replace dx with? Well, just off to the side here, x is f of t, right? So what would dx be? We used to do that. Remember how we did that? To get dx, well, let's do it this way then first. Do we know how to do dx over dt? Wasn't that the same as f prime of t? So then what does that make dx? F prime of t dt, that's just off to the side here. So what can I replace dx with? F prime of t dt. So how would you find area under that curve if the curve is given parametrically? You use this instead. You take the integral from alpha to beta, those are your t values of g of t, times f prime of t dt. But now I'm going to throw a little wrinkle into it, because it's not just going to be a curve and the x-axis. It's going to be area between two curves. So it's an area bounded by the curve x equals t minus 1 over t and y equals t plus 1 over t. That's one curve given parametrically. Okay? And then the other boundary is going to be that line here. If you wanted to, you could say x equal to t, y equals 2.5. Where's the t in that one? Well, there isn't one. That would be the parametric version of that line if you want it. So those are my two curves. Okay, the first thing we always did when we found areas between curves in the past is we wanted to see where that was, because to get the limits of integration, don't you have to check the intersection points of the two curves? Okay, I wrote the second one this way so that I can do it parametrically. Just let x equal t, let y equal 2.5. I guess if you insisted on putting a t in there, it'd have to be t to the 0, wouldn't it? Okay, let's see what we get. Okay, getting rid of that beautiful orthogonal curve. Boy, that's painful for me. But you have to move on sometimes. Okay, zooming in so you can see it. I first type in the curve t minus 1 divided by t. And to go with that, to complete the curve, the y has to be t plus 1 divided by t. And we'll just kind of look at what that one is in the standard window. Now to really see what that curve is, you need a bigger t window. If you go from minus pi divided by 2 and then to 2 pi, you can get a better picture of what that really is. So here's graphing it. Yeah, it's still not quite good enough to suit me. I want to change the window from minus 3 pi to 3 pi, okay? Because I'm not seeing enough of it yet. So there's one more time. Hopefully that gives a little more of it. Here's one branch of the curve. And there's another branch of the curve. Okay? Do you recognize that curve? I increased the t value so you could see more of the whole picture. You get this piece on top and you get the symmetrical piece on the bottom. That was called a hyperbola. That's just an aside. Called a hyperbola. Two branches. And can you see there's an asymptote that comes up here and an asymptote that hits there? That's called a hyperbola. that's not really relevant to the problem, but what I wanted you to see is more of the picture. Now I've got to put in my other one where x is equal to t and y is just equal to 2.5. Okay, now I'm going to graph them. And as you know, the other one's going to be a horizontal line, 2.5 units up. And I'm trying to find the area between the line and the other curve. So you see the bottom branch is irrelevant here? It's that little piece right in there. Let's zoom in on it a little bit more. Zoom number 1, and we'll just kind of do our box. We'll make that one corner, and that'll be good enough. Okay, so we'll zoom in on just that much. So there's your parabolic branch, and here comes the horizontal line, and you can clearly see a nice little piece of area in between, not real huge, but I want to find how big is that area between the line and the curve, okay? Well, we always recommend, this can get really tricky, because when we did this in calculus earlier in this semester, do you remember when we set up the integral, it was curve on top minus curve on bottom, remember? So I drew the graph to establish that the line is on top and the hyperbola branch is on the bottom. But then I need my limits of integration, right? So I need to find where these two intersect. Now, sometimes you can get it right off the calculator if they're nice answers. If not, you have to do it algebraically. We'll probably do it both ways if we can, except when I went to math, intersection's not highlighted. Is it on yours? I lost my intersection. There's an intersection on number 8, I believe, I mean number 5, but mine is gone. Is yours there? Maybe we can get it back. I don't know if there's something about the format. Let me see. Coordinates. No, that looks okay. Sequential, that's okay. Is there something turned off that I need? I don't know why intersection isn't active with parametric, because it's there, but it's been turned off. And I'm not sure how to turn it on, or whether that's just automatically they're not going to let you do intersections off from the calculator. I got to explore that a little bit more. So I guess that's kind of out of the question, at least at this point, unless we figure out a way to get intersection turned on. But I do know this, that I have this branch of the hyperbola coming, and then I have this line, and I'm looking for the area of that shaded part, right? I need to find the points of intersection so I know how to set my limits of integration. So what do I have to do? We'll find when the two curves intersect. Well, when the curves intersect, shouldn't the y's be the same? Okay, so in one case I have y equals t plus 1 over t, and in the other I have y equals 2.5. So I just said 2.5 has to equal t plus 1 over t, and then I solve for t. So what am I doing here? I'm looking for intersection points so I can set my limits of integration. Okay, multiplied each side by t, got 2.5t equals t squared plus 1. Got one side equal to 0 because it's a quadratic, and had t squared minus 2.5t plus 1. Well, if I'm going to factor, I don't like decimals, so I multiplied everything by 2. I got 0 equals 2t squared minus 5t plus 2. And then I was hoping that was factorable, because if it is, then I'm going to have some nice answers. If it's not factorable, then I'll have to use the quadratic formula. But I believe that thing is factorable. A 2t and a t for sure, right? And I think a minus 2 here and a minus 1 there would do it. Does that look okay to you? I know I'm going to get a 2t squared and a plus 2, but am I going to get a minus 5t in the middle? Indeed we are. So the intersections occur when t is a half and t is 2. All right, that tells me the t values, but it doesn't give me those points. So, if t equals a half, what is x? According to the parametric equations, it's 1/2 minus 1 over 1/2, which is like 1/2 minus 2, which is like minus 3/2. Which point do you think has an x-coordinate of minus 3/2? I would guess maybe the one on the left here. Oh, but what's the y-coordinate?
3x.
No, it's on the line 2.5. Isn't it on the line, and the line is y equals 2.5, isn't it? Okay, you know what I think the other point is, just because of the symmetry of the situation? That would be my guess. Of course, I could test it. If t equals 2, the other possibility, x is going to be 2 minus 1/2, which is indeed 3/2, but we sort of could see that from the symmetry. Okay. If I wanted to do this in Cartesian, I am ready to find area. Because it'd be the integral from minus 3/2 to 3/2. And then it'd be curve on top, right? And the curve on top is y equals 2.5. Minus curve on bottom, but I don't know what that is. So I'm just going to let it be y. That's what it would have to be if I did it in Cartesian. I'd have to take the curve on top, the y on top, minus the y on the bottom. I knew that y on top is 2.5, but the bottom one I don't know. So if I wanted to continue in this manner, what would I have to do? Find a Cartesian equation for y, and then I could finish it. Some people say, I think I'd just do it that way. Well, I plan to finish this if I have time, but I'm going to do it parametrically first. Okay, if I want to do it parametrically, then what are the limits in parametric form? Well, what t value produced minus 3/2? 1/2 did. And what t value produced 3/2? Okay, 2.5. And see, this is going to be easier because I know what y is in terms of t. See, I don't know what it is in terms of x, but I do know what it is in terms of t. And if you don't believe me, there it is right at the top of the screen. There's y in terms of t. That's why I'm doing this parametrically, because I know what y is in terms of t. It's given to me. I don't know what it is in terms of x without doing some work. So what do I put in for y? T plus 1 over t. Make sure you put that in parentheses. All right, now I got to substitute dx. Well, that's no big deal, because I know what x is, right? So what's dx? The derivative of this times dt, remember? Okay, so just off to the side here, I know that x is t minus 1 over t. I'd probably write that as t minus t to the minus 1. So that means dx over dt is going to be 1 plus t to the minus 2, isn't it? So what does that make dx then? 1 plus t to the minus 2 dt. And that's what goes right here. 1 plus t to the minus 2 dt. That's the integral I have to evaluate to get the answer. Okay, we'll let the calculator finish that one for us. We could probably integrate it by hand if we were really hard pressed, but right now you just look pressed, not hard pressed, so we'll do the calculator. You see where we got the integral from? So we started with the basic principle, it's curve on top minus curve on bottom. And then we just converted all these pieces to parametric form. And then we got something to type in our calculator. So now we're going to zoom in and see. Okay, going to the home page, grabbing F3, number 2. I got to type in that integral that was on the screen just a minute ago. And the integral, watch your parentheses, had parenthesis 2.5 minus parenthesis t plus 1 divided by t, parenthesis, parenthesis. I'm going to put in my times sign because I know this calculator. And that was times the quantity 1 plus t raised to the negative 2 power. And I want to integrate that with respect to t, and I want to go from 1/2 all the way to 2. And the answer is, I press diamond enter, approximately 0.9774, right? So the area between the line and the hyperbola is about 0.9774. Okay, let us record that. So we can find it back. Okay, now you don't have to copy down or anything what we're about to do, but I want you to see what would happen if I took this same integral right here and tried to finish it Cartesian. To finish this with Cartesian, I got to replace y with a function of x, right? Should get the same answer. So here's the work, so you can see why I went parametric, okay? I have the integral from minus 3/2 to 3/2. I know I have to do 2.5 minus y, but I got to find y in Cartesian. Well, this is what I know. I know that x is t minus 1 over t. I know that y is t plus 1 over t. How do we convert parametric to Cartesian? You solve for t in the substitute. This is going to get messy, see? So I take this equation and I have to solve for t. Okay, I first multiplied everything by t. Tx equals t squared minus 1. But I got to solve that for t. 0 equals t squared minus, well, I'll make it xt, and then minus 1. Solve that for t, can you? want to solve that for t in terms of x. Can you do that? Well, in previous sections, they were kind of nice to you because they made sure the equation was linear, so you could always solve for t. What is this one? Now, I think your calculator could probably solve it for t. But I solve for t by using this. Have you seen that? Okay. What is the value of b? I'm solving this quadratic. What's the value of b? It's the coefficient of t. I'm solving for t. What's the coefficient of t?
Minus 6.
Okay, so minus b would be x. What would be b squared? Minus 4ac over 2a, right? So what is t? It's x plus or minus the square root of x squared plus 4 over 2. There's t in terms of x. But now I got plus or minus, right? Which one am I going to pick? Well, you got to decide where you're at. Now, if you go back to the picture, here it is. X could be either positive or negative, right? But y has to stay what for both curves? Positive? Okay, y is t plus 1 over t. Now if I want this to be guaranteed to stay positive, keep t positive. Take the plus probably. Okay, so here's getting y right over here. Y is equal to t plus 1 over t. But t is x plus the square root of x squared plus 4 over 2. Then I have to add to that 1 over that mess. And so y ends up being x plus the square root of x squared plus 4 over 2 plus 2 over x plus the square root of x squared plus 4. There's your Cartesian equation. Now do you see why I stuck with parametric? But now that we went this far, we got to see at least if we get the same answer, right? Now, what if I had something like t cubed here? Good luck, right? Trying to solve for t in terms of x. I mean, with a quadratic, I could at least use the quadratic formula in a way you're not used to using it, but it does work. Okay. Now we got to go back to this integral right here at the top of the screen. We got to replace y with what's in the circle here. Okay? So here we go. The area should equal the integral from minus 3/2 to 3/2 of 2.5 minus what we found for y right here, which is x plus the square root of x squared plus 4 over 2 plus 2 over that same thing and then dx. If I can manage to type that in my calculator, I should get that same answer I got before, which was about 0.97 something. Okay, now we're going to see if we can type that in. So we're going to lose it when we zoom out, in. But the nice part is the old answer is still on the screen, so we got something to compare to. So we just clear this. We'll go to F3 number 2. We'll put in a parenthesis and say 2.5 minus parenthesis x plus the square root of x squared plus 4 parenthesis, divided by 2. I'm glad I got the pretty print. Too many parentheses. Going to mess this up. Parenthesis. X plus square root. That needs its own private parentheses. I'm going to integrate that with respect to x. Hopefully I got my parentheses right. Ooh, I think I'm missing one. I'm going to put one more there. Hey, when in doubt, add one. That's hard to keep track. And this time I'm going to go from minus 3, oops, halves, and then all the way to 3 halves. Diamond enter. Hate it when that happens. Where is it missing one? Maybe I don't want that one there. Oh man, why does it want one right there? Doesn't make any sense. After the comma? Ah. I hate calculators. You didn't hear me say that, did you? Okay, the integral. I got to start counting parentheses. I think I will
You have 2 parentheses.
get rid of
before
that
your
one.
x. 2.5 minus parenthesis, parenthesis.
Yeah, I did that because I got to subtract an entire quantity, and that one right there is for the numerator. See, the numerator is 2 things. That one right there is for the radical, and that's the end of the numerator divided by 2.
You might need another one after the 4 parenthesis, parenthesis, right before your division sign.
I've got one for the radical.
Yeah, you have one for the radical, and then you have one for the quantity. But then there's just that one floating right around.
Right there?
Yeah, I think that might work.
Divided by 2, and then 2 divided by that entire thing. Now let's try it. It's busy. It's always a good sign. But it's not the right answer.
No.
So it can't be right. Why did I even try this? Let me see, my limits of integration are right. Oh. Just look at the pretty print. You're not subtracting the entire quantity, right? I'm only subtracting the first one, and then I'm adding the second one later. So what do I need? Another parenthesis there. And another one when I introduced it. But those are the ones I got rid of. Okay. I can't give an exact answer, obviously. 0.9774. So get it typed in right, at least you get the right answer. And now you can see from the pretty print it is the right integral. Okay, so you can kind of see why I just stuck to parametric. But it does work, doesn't it? And can you see where you could get into a real bind trying to get the Cartesian version of y? I mean, this one was not fun, but it was doable. Stick to the, watch the area problems, they're tricky. I recommend you write in Cartesian first, and then convert it to parametric and then do it. Okay, there's one other simple little concept we have to do here, and that is finding arc length. Okay, we first do our recall. The length L of a continuous curve from C to D is given by an integral from C to D, and the square root was 1 plus dy over dx squared dx. Remember that arc length formula? I'm just kind of grabbing that from what we did before. Or we could also do it by going from f of c to f of d, and doing 1 plus dx over dy squared instead. And sometimes that was easier to fill in. So it's either the square root of 1 plus dy over dx squared dx, or 1 plus dx over dy, the quantity squared, dy. Okay, so we start with that, because that was the arc length formula we used in Cartesian. Okay, to convert it to parametric, we suppose that x is f of t again, and y is g of t, and t goes from some a to b. Okay, starting with what we have above, we have an integral from c to d of 1 plus the quantity dy over dx squared dx, okay? The first thing I want to do is change that last dx into the square root of dx squared. Are you okay with that? And why did I do that? Because I wanted to get the dx back into the radical. If I bring it inside the radical, you got to distribute it. What is dx squared times 1? What is dx squared times dy over dx squared?
Keep that up a little bit. Thank you.
So if I distribute that, we end up here. The reason I wanted to do that was dx, well, isn't x equal to f of t right there? So what is the dx then? Well, we've done that before. Dx would be like doing f prime of t, right? So in this particular case, I can write it as the square root of dx over dt squared plus dy over dt squared. But to maintain equivalence, I have to put dt squared here. So if you were to, distribute this back, wouldn't you be right back to the previous step? But I didn't put limits of integration in because now I'm working with t, so they switch through a to b because that's my t limits. Okay, now that dt squared that's under the radical there, that can be moved outside. This is still under the radical. So this takes me to the final answer, which is the next blank right here. If I fix that up, I get the integral from a to b of the square root of dx over dt squared plus dy over dt squared and then dt. Official formula for arc length given parametrically. Okay, in my example, x is equal to this and y is equal to that one. And basically, to make it easier to find dx dt, I'm going to write x in exponential form. So that would be 1/3 times what? What's another way to write the square root of something cubed? Three halves. And the next one is y equals t plus 1/2 t squared. So that makes the dx dt a little easier to do. Exponent times coefficient. What's 3/2 times 1/3? And then you take 2t plus 3 to 1 lower power. What's 3 halves minus 1? And then you got to multiply that by the derivative of what's inside. So what does this eventually become? Just 2t plus 3 to the 1/2. Okay, now dy over dt. Well, derivative of t is 1. The derivative of 1/2 t squared is what? Right? Now I rigged this to come out really nice. Because what is L now? Well, if we check the formula right at the top of the screen, I got to take what I got for dx over dt and do what to it? But I do need this, and according to this, we're going from 0 to 3, right? Okay, what happens when I square dx dt? You're just going to get 2t plus 3, right? Because it's to the 1/2, and I'm going to square it. But I still have to add 1 plus t, the quantity squared, and then dt. And to show you how carefully I rigged up this example, you're not going to believe this. I worked more hard at rigging it up than doing it. L is the integral from 0 to 3. Under the radical I have 2t plus 3. But I also have 1 plus 2t plus t squared. You're going to be proud of me. Then I combined like terms under that radical and got a t squared. How many t's? 4 of them. And the constant? Now if you look carefully at that trinomial I got, that thing factors. That's nothing more than t plus 2 the quantity squared. What nicer thing than that could happen? Because what's the square root of t plus 2 squared?
T plus 2.
It's t plus 2 as long as t plus 2 is positive, and I know it is because I'm going from 0 to 3. Okay. So it's really the integral from 0 to 3 of just t plus 2. Well, how easy is that? That's just t squared over 2 plus 2t, evaluated from 0 to 3. So fundamental theorem says put in the 3, and I got 9 halves plus 6. Then I have to subtract what I get when I plug in 0, and I got 0 plus 0. Final answer? 9 halves plus 6. And I did fine right up to that point, and then I got stuck. And then my friend said, well, like 6 is 12 halves, isn't it? And I said, yeah, but who cares? Well, come on, 6th grade, you have to get a common denominator to add. I slept through that class. Well, trust me, the answer is 21 halves, he said. And you know what? I did that whole problem without ever what? Touching a calculator. You mean you can actually do calculus without calculators? Sometimes. Okay, we're going to save 637 number 52, but you should have enough background to pretty much handle 10.2. Now the derivative work in tangent lines, that's pretty straight. It's pretty hard to mess that up. But as soon as you have to find area, be careful. Oh, it's so easy to mess those up if you're not focused. Okay? Arc length, piece of cake. I mean, how can you go wrong? You just saw it happen. I mean, we did this whole problem in like 2.5 minutes. And we didn't even get help from the calculator, so. But watch those area problems. Make sure they're set up so you can handle them. Okay, see you back Monday. Same time, same station. And remind me we have to finish up number 52 on Monday. And then from there we'll probably head into chapter 9. We're in actually pretty good shape because we've got 2 weeks to go. That's 6 sessions. And in 6 sessions, I have to cover 3 sections.
Yes.
So that's not bad. So we kept pushing along, but eventually, at the end, you don't have to rush, which is kind of nice.
You got the place by a bridge.
But don't forget the project, right? The lemon project. It's going to be a nasty weekend. Good time to explore some of that. You have all the background you need to do the whole thing now, because first half is the series stuff, and the second half is doing some parametric stuff. Shooting some missiles, riding a bicycle, stuff like that. Okay, we'll see you.